We will continue with the next stage, that is the anti-series differential pair, that it is extremely important in analog circuit design. So this stage is formed by two ABCD blocks that have been connected in what we call the anti-series. So the anti-series is like this. The input one will have plus minus, and the minus of one stage is going to be connected to the minus of the other stage. And the same we take at the outputs. The negative output of one stage is going to be connected to the negative output of the other stage, and this has interesting properties for us. We're going to analyze these properties using ABCD parameters. So conceptually, we can draw these as transistors if we want to visualize this as a two amplifying devices. One will look like this, the other will look like this. That will go to the output here, and then we will have the sources connected here. Okay, so if we implement this with one transistor, this anti-series differential pair will look like this. Okay, so instead of doing circuit analysis on this kind of configuration, what we can do is to reuse what we have learned about ABCD blocks. So we're going to use two-port network theory to find the final two-port parameters of this configuration. So we are going to be finding this one. Okay, so we start. There is a total input voltage and there is a total input current that flows through this combination, and then the input current is entering here and it is leaving like this. So we have a number of equations here. For the first one, it is that the input voltage will be equal to VA1 minus VA2. Okay, so this is our first equation here. The other equation that we will have is that this current that it flows inside this combination is equal to I1, the current entering in the first block, and this current has exactly the same amplitude but flows in the opposite direction to I1. So I1 is going to be equal to minus I1, I2, that will be I2 here. Okay, so we have the first equation here, and another thing that we can see here is that due to the symmetry, these two blocks are exactly the same. We have that the VO1 will be only half of the total voltage, so we're going to use this very soon. Okay, so we go forward. Remember that for the parameters, for the ABCD parameters, V in is equal to AV out plus V E out, and E in is equal to CV out plus DE out. So we're going to expand this equation that we have just created. So we start with the first one for the input voltage. That will be first this one here, AVO1 plus VIO1. So we have this part here, and then we expand this one. That will be minus AVO2 minus VIO2. And then we can use this equation here to replace IO2, so that we can put everything as a function of only one current. So we have that VE is going to be equal to A VO1 minus VO2 plus B, and that will be IO1, and we just use this equation. IO2 is equal to minus IO1, so that will be plus IO1 here when we multiply by minus 1 here, and that will already give me something very interesting. VO1 minus VO2, it is the total output voltage, it is this one here, so this is VO, and this IO1 it is exactly the same as the output current, so that will be 2 times beta IO. Okay, so we are there with this equation. Now we go to the next equation. With the next equation we have that the input current, it is going to be equal to E1 or the same as minus I2, so we can expand these ones, that will be equal to CVO1 here plus DIO1, or this is equal to minus C by 1 minus DO1. Now we can remember this is totally symmetric, so this output voltage has to be equal to half of this voltage has to be equal to VO1 or VO2, so we can replace here. So we have EE is equal to C VO divided by 2. So we have this one here, and the EO1 is equal to EO. Okay. So after this replacement, we see that we have totally defined the ABCD parameters of a anti-series differential pair. So the A parameter has not changed, it is the same as for a single stage. The transconductance parameter has changed. Okay, now it's 2B. The transimpedance parameter has been halved. That means that has increasing amplification. This has decreasing amplification, it has increasing amplification. And the current gain is exactly the same, has not changed. And that will be the equivalent circuit for the equivalent ABCD parameters for my differential pair. Okay, so this is from the amplification point of view. Also, we are going to show a model that we will use for small signal for this one based on these ABCD parameters. But first, let's talk about how does it actually work. So the differential pair, even though we use two transistors, we consider it a single port network, and basically we have differential pair, transistors are here. We consider this one as a one block, a 2-port network block, and the small signal model that we're going to use is the following. So we saw that we had A, 2B, C divided by 2, and D. What does it mean, this? First, it means that we will have exactly the same voltage gain. So we might think that because we are having 2 transistors, we will have more voltage gain. It is not really true. We will have exactly the same voltage gain. We have that the transconductance will get deteriorated. The transconductance have been halved. Okay, remember that the ABCD parameters are the opposite to the gains. So the transconductance have been halved, and then we notice that the transconductance has been halved because we only have half of the transconductance in the model. we have that the transimpedance parameter has been halved. That means that it's being improved, and the transimpedance parameter depends partially on the input impedance in the transistor. So because we multiply the current by this input impedance here, so we say that this stage has twice as much input impedance as the single stage. So our model, to model that, we will have this capacitor divided by 2, CGS divided by 2 here. So another way of seeing this is that we have a capacitor here, and now that means that the total capacitance that we see here will be basically CGS divided by 2. We just take in consideration this CGS. Okay, so the impedance has increased by a factor of 2, the input impedance. And then we have the output, and the output we have 2 resistors. So we have one RDS here, another RDS here, so at the end of the day we will have 2 RDS following at the output. And now think about this. Now the voltage that I'm going to amplify is this one here. I cannot call it VGS anymore, I will call it V1. V1 gets multiplied by GM over 2, and then it gets multiplied by a load of 2 RDS, so the total voltage gain here is I expected equal to GM divided by 2 times 2 RDS GM RDS, which is the same as for a single stage, and it is already predicted by this. So this is for the small signal model. Now let's see another interesting properties of this. This is when I amplify the signal in a differential way. So why is this stage interesting? Well, it already applies some interesting correction when we talk about common mode amplification. So let's take a look very quickly how does this happen. So in a single transistor, the output voltage, as we saw before, it has a quadratic dependence. We have a quadratic dependence due to the nature of the transistor. In strong inversion, there is always some quadratic dependence there, but it can actually have other dependence than quadratic. We can model this as a Taylor polynomial, in which higher order distortion might appear, higher order dependence on the polynomial might appear. And then we can see directly that a single transistor has an amount of distortion that it is always going to appear at the output. Now, when we put 2 transistors in anti-series, what we're going to have is that here, precisely at the center, we can assume that it is going to exist an AC ground. And my input voltage will be divided in 2 parts here, and I will be amplifying these 2 parts, one by one transistor and one by the other. Okay, that is for a differential signal. Then if we pass this voltage to this transistor, it will generate an output that, as I expected from the behavior of my transistor, will have distortion, second, third order, fourth order distortion, etc., etc. Now what it is interesting is that the other will also operate with the negative part, but it will produce second or even order distortion with exactly the same sign as the other device. Okay, and even the offset will be the same here. So even order distortion will be the same in both sides, assuming that the devices are identical. it is only the odd components that are different because they come with different sign. So when I take this output signal differentially, I can see that the even components subtract, they basically disappear, and that is how offsets and even order distortion, it is basically corrected when I use the differential pair or the anti-series. A very important property. Okay, so the differential stage, the anti-series stage, rejects even order distortion and offsets. So what happened with the common mode input signals? So we have studied the differential signals, but when we apply common mode signals to the input of anti-series stage, what will happen is the following, and now we are going to use as a help the actual implementation of the differential pair. So we will have some resistance connected to one of the nodes and going to ground, and then we will have some loads connected to the outputs. So this is the typical scenario for a differential pair. And what we can do here it is that we can split this resistance in two resistors here without changing the circuit. So basically this is exactly the same circuit. Now there is no current flowing here because the circuit is completely symmetric, and the voltages, they are common mode voltages, they come same voltages to one input to the other, so this circuit is totally symmetric. So there is not going to be any current flowing in this connection, so I can actually delete it, and we will have the following circuit. In this circuit we have two common source amplifiers with the series resistance, something that we have already studied before. If we extract the gain from the input gate to the drain of any of these two configurations, we will see that the gain it is equal to minus RL to RS if we take the asymptotic gain as a first approximation. And this already tells me something, that signals that come the same at both inputs, what we call it common mode signals, are attenuated by the series resistance that we have here. So differential stage normally are designed to have a very large resistance or impedance from the source to ground, because that is what it makes possible to reject the common mode signals that are normally detrimental for the performance of our system. Now, beside the differential pair, there is other interesting connections that are very, very common, and one of these ones, it is a differential pair that has only one output. Okay, so one way of implemented the differential pair with one output, it is just taking directly. For instance, we have the differential pair like this. To ground one output and take the other output. Okay, so in many configurations this will work, and this will be enough. But there is interesting variant of that configuration. Remember that it is not always that we need a differential output. In many of the feedback configuration that we have studied, we just need one output to produce the negative feedback. There is a very interesting way to reuse both outputs of the differential pair, and this is by adding a current mirror. Okay, so instead of grounding one of the outputs, we can take all the current that is flowing through this one and then mirror it towards the output, and then we will be reusing the current. Okay, so in this way it will increase my transconductance, because now we have both transistors that are contributing with the transconductance. So I will have a better amplification with this if I only take half, like in this particular case. Another stage that it is quite important for us, it is the cascade stage. And in the cascade stage I also use two transistors, but I connect the transistors like this. Okay, so I connect the transistors, I stack transistor in this way, and then if I connect the transistors in this way, what I am actually doing, it is that I am stacking a common source transistor. This is a common source stage. I am stacking to a and this is the input. I am stacking to a common gate. Transistor. Yeah, and then we can analyze these stages using also ABCD parameters. So for the common source stage, we have that the parameters, the ABCD parameters were approximately -1 divided by GM RDS. Let's make this a little bigger. So for the common source, we had that the ABCD parameters they were -1 divided by GM RDS. The beta parameter at -1 over GM. So when there is no source resistance, we assume an ideal source resistance for the current amplification. These parameters will be 0. For the common gate, we have that it is basically the same as for the common source, but the parameter D is equal to 1. The other parameters are the same. So this is 1 because it is a current buffer. Okay, now what we're going to do, it is we're going to do like this. We're going to use the A, B, C, D parameter of the common source here, and then we are going to cascade it to the A, B, C, D parameters of the common gate. Okay, and then we will find the resulting ABCD parameters, and that basically will be the matrix multiplication. Okay, we will find the matrix multiplication for this. So we will have A1, B1, C1, D1, A2, B2, C2, D2, A1, B1, C1, D1, and there will be A2, B2, C2, and D2, and then when we do this multiplication of matrices, let's see what will happen. So let's take the first one. So we take this row, we have to take this row and this column, so we multiply, and then for the common gated, these ones are change the value. It's the only difference that it really has. And then what we have is that when we multiply, this will be equal to 1 divided by gm square rds square that will be the first voltage gain, or the current. It will be multiply, we will use this row and this column, and that will be minus 1 over gm square rds and minus 1 over gm, and then for the other two there will be this row and this column, that will be 0, this row and this column, that will be 0 also here. Okay, so we can see almost directly that we have an improvement in voltage gain, that became 1 over gm rds square. So the total voltage gain here, the voltage gain for the cascade amplifier, will be minus gm square rds square. So what has happened here, basically this transistor here, we call it M1 and M2. See here M2. This transistor sees transistor 1 as a big resistor. That is a resistor, and that is going to be RDS1 here. And we have talked about we'll talk about a little bit about the loop gain for this transistor. The loop gain for this transistor is GM time RDS approximately, and if we use circuit theory and we find the output resistance here, okay, that output resistance will be equal to RDS2, that is the resistance here, RDS2 times the loop gain, approximately that will be GM, this is GM2 RDS1. Okay, so that is what the circuit theory will tell me, and this is for the output resistance. Now if I connect instead the first transistor here like this is M1 and an input voltage in. This voltage will be converted into current. It will be V in multiplied by Gm, this current, and this is the current that it is going to flow like this when we connected the cascade here. It's going to flow here and get multiplied by the output resistance. So the V out will be equal to minus Gm1 multiplied by R out, and that will be minus Gm1 times RDS2 Gm2 RDS1. That will be equal to, if we assume that those transistors are the same, then that will be GM square RDS square. And this is just a simplification. The real circuit analysis for this is much more larger. So, but we don't need to do it because now we know that we can use the ABCD matrices. When we extract the ABCD matrices, then we can just do matrix multiplication to get exactly the same results. So how we model this? For low frequencies, we have the transconductance from the first transistor, and then we have the output resistance at the output of the cascode, that it looks like this, and then we get all the gain. Now there is an important detail here. What happens at the higher frequencies, and this is one of the properties of the cascode, that it is very nice, is that that Miller capacitance that we talked before doesn't get multiplied by the whole gain like in the common source amplifier. It just gets multiplied by the small value. So we see the amplifier now like this. CGD. Okay. So the amplification that I have, I have a V in here, to this node Vx, it is going to depend on the impedance that I see in this direction, theta in. So I need to calculate that impedance that I see in that direction. So let's do it very quickly. Let's assume that this BGS, this is BGS, that the transistor only looks like this, with some loads that we don't care right now, RL, and then I put a test voltage source here, and then I will calculate what is the test current here. And my impedance that I see in that direction, R in, is going to be equal to V test divided by E test. So we have that VT, okay, it is this voltage to ground, is the same this voltage to ground, so it has to be equal to minus VGS. Okay, and if we do also node analysis, we have that IT has to be equal to minus GM VGS, so all the currents that come to this node have to be equal to 0. Then I can just replace, so that will be IT minus GM minus VGS plus oh sorry, that will be VT minus VT here, change this, and VT divided by IT, that will be equal to 1 over GM. Okay, so this is a very important result. Every time that I see, let's put it here, every time that I see an amplifier in this direction, the output impedance will be around 1 over GM. So in this direction I see 1 over GM. In this direction here down I will have RDS, RDS are much larger than 1 over GM, so the total gain that I will have from the input to this node Vx will be approximately, so we have V in gets converted into current, GM1, we call it M1 and this M2, Vn get multiplied by GM1, we have this current here, and then this will get multiplied by all the impedance that we have at that node. That will be 1 over GM2 in parallel to RDS, but as we mentioned before, this is much larger, so that will be Vx is equal to, so this resistance is much larger, so we will have that Vx divided by V in will be equal to, there is a minus sign here, GM1 divided by GM2. Since the transistors are the same, currents are the same, sizes are the same, the transconductances have to be the same, then the gain will be approximately equal to 1 here, if RDS is much larger than GM2, which is normally the case. So from the Miller point of view, this capacitance has only an amplification of 1, a factor of 1. So if we revisit the Miller effect, the pole that we have at the input, that pole was Rs, CGS plus CGD 1 plus AB. So this factor will be equal to 1 in a cascade. Will be equal to 1, that means that there is only going to be 2 CGD that is being added to the pole, and that is how we model this one here. We add only 2 CGD here. Now there is no interaction from the input to the output through CGD, so this is open. We keep it open, which is very nice. We have basically reduced the interaction that happened through CGD. That was very problematic. And then at the output, on the other hand, we have this CGD here, CGD that it is connected to ground, that appears here. Yeah, so this will be the model for our cascade amplifier. So very interesting. Increases the gain. It reduces the interaction from the input to the output, and it reduces also the Miller capacitance at the input. So the cascade is a very powerful stage that we will be using in analog design. Now there is another stage also that it is possible to use, and it is called the long tail pair, and it combines a common drain stage and a common gate stage, and it is very similar to a differential stage, so we treat it kind of similarly. We see here that CGD, it is basically connected to the minus terminal of the input and of the output, and that is very interesting property because there is no Miller effect with this capacitor. We have that the input impedance is also the same as in a differential pair, is CGS divided by 2. It did increase the input impedance. We see here also that it shares with the differential pair the half of the transconductance, because now we are having just a factor of 2b in the ABCD parameters, so we have half of the transconductance that is working. And yeah, we have also that this capacitance appears here, CGD, from the output to the negative input and output. One of the things about this stage is that it cannot be used alone, because as you might see here, this is a common drain. It means that the positive voltage here becomes also positive here. This is a common gate. The common gate, the positive voltage at the source becomes also positive at the drain. So there is no sign inversion. We don't have sign inversion in this stage. So we will need to use with another stage in a multiple stage amplifier. Very interesting point about this stage, there is a much reduced influence of CGD in this stage. CGD, as we mentioned before, is a middle capacitance, can change a lot the position of the poles. It coupled the input to the output, and it is also nonlinear. Even though it is overlap capacitance, the moment that it gets multiplied by the gain, if the gain is nonlinear, it will also create a total nonlinear capacitance. We have another stage also that it is interesting. We have that stage. It is the antiparallel stage. An antiparallel stage can be formed, for instance, with an inverter connection, like this. And conceptually, it works like this. We have A, B, C, D, A, B, C, and D, and then we have that the inputs are connected together, the outputs are connected together, and then these ones are also connected together. Like this. So that will be the two-port model. And if we do a similar analysis that we did for the differential stage, we will have that our resulting ABCD parameters will look like this. The voltage gain is actually the same. We will have at the current gain increases by a factor of 2. The transimpedance factor decreases by a factor of 2, and the current gain is exactly the same. So those will be the main blocks that we will use to implement the amplifier. So we have this antiparallel that looks like an inverter. We have a long tail pair. We have a cascode. We have a differential pair, either completely differential or with a single-ended output. And we will have current mirrors. And in some cases, we will also use series stages and shunt stages. Then we will have basic configurations, like the common drains, common gate, and the more useful will be the common source stages. Okay, so that's for today.